Chemistry, we're moving on to Unit 3. This is going to be on the subject of intermolecular forces, and it is a very heavily tested subject on the AP exam. So we've learned there's three types of chemical bonds. The two that we actually looked into were ionic and covalent. The type that we will get into later when we talk about metals is metallic bonds. So you see over on the left, the way metals bond together is through metallic bonds. And they do this through what's called the electron C model. And you notice that those electrons, those are valence electrons, and they're moving around between different atoms. They're not attached to one atom, nor are they simply being passed from one atom to another and then staying there. They call this the electron C model because it resembles fish swimming around in the ocean. So this is the way metallic bonds work, and we'll study that in more detail at a later time. The second way is the way that we studied, which is ionic bonds, and that's when an electron gets passed from a metal over to a nonmetal. That's the strong guy, weak guy analogy. That makes the nonmetal an anion, negatively charged, and it makes the sodium a cation, positively charged, and they're attracted, they stick together. And the Na and the Cl are not an independent unit. They're like bricks in a wall or apartments in an apartment building, and they fit into that structure down below called a crystal lattice structure. That's why salt, table salt that you eat with your food, is a cubic shaped, when you look at it, is cubic shaped. Then finally there are covalent bonds, and that's when electrons share. So you see the oxygen and the hydrogen are going to bond here, and they're going to share electrons. Covalent bonds form molecules, structures called molecules. These are independent structures. So one water molecule can move in one direction when you boil water, and then another can move in a different direction. So they're independent structures. They can move about independently. So whether they stick together as they do with ice, or flow around each other like as with liquid water, or they separate as with steam or vapor in gas form, that's what this subject is all about. It's what determines whether the intermolecular forces cause molecules to stick together. So only covalent bonds form separate structures called molecules. Intermolecular forces determine whether molecules stick together or not. Key point, intermolecular forces are much weaker than covalent, ionic, or metallic bonds. So a solid retains its own shape, such as an ice cube. It's incompressible, you can't squeeze it down, and it does not flow. Liquids take the shape of the container, so a certain amount of water can either fill up a tall, narrow glass or a short, wide glass, but it's the same volume of water. It's the same amount of water. They're also incompressible, like as solids are, and they diffuse slowly in other liquids. So think about putting a drop of food coloring into a glass of water. Gas takes the size and shape of the container. So the gas molecules inside a bottle of perfume on a warm day will be contained within that bottle, but if you take the top off 15 minutes later, those perfume molecules, you'll smell them all throughout the room, and they're taking on the size and shape of the room. They can flow and they diffuse in gas rapidly. So IMF, intermolecular forces, are a battle between kinetic energy and Coulombic attractions. Kinetic energy caused by higher temperature and assisted by low pressures allow molecules to separate. Coulombic attractions are the electrostatic forces of protons and electrons that attract atoms, ions, and molecules to each other. So these two are battling each other. The Coulombic forces are predominant, then the molecules will stick together. If the kinetic energy overwhelms the Coulombic forces, then they will come apart. So generally, matter moves from gas to liquid to solid in two ways. One is by reducing temperature, so molecules decrease energy and move closer together. So if they have a lot of energy at 20 degrees, that's normal room temperature, they can fly around. But if you lower the temperature down to the freezing point of water, they'll eventually lose energy, and they'll come and they'll stick together like that. The other way is just by increasing the pressure while keeping the temperature constant and squeezing the molecules closer together. So this is just kind of the brute force way to get them to come together. You just squeeze them together. That's higher pressure. If the kinetic energy overwhelms the Coulombic attractions, then the molecules separate and exist as gas or vapor. So this would be water molecules in vapor form or gas form. They're moving around randomly. The reason they're changing directions is they may be hitting other molecules, they may be hitting the sides of a container, or there might be heat coming up from below that's causing them to move about. If the kinetic energy and the Coulombic attractions are about equal, then the molecules stick together, but they can move around each other. So these molecules form liquids. So liquids, the molecules stay in contact with each other, but they can slosh around. When you slosh water around, they can move around each other. If the kinetic energy is low compared to the intermolecular forces, then the molecules will stick together in fixed places. This produces a solid. Hydrogen sulfide, this is just one example, is H2S, has a freezing temperature of negative 82 degrees centigrade. So that would these molecules would have to be below that temperature. Even molecules in a solid, though, move. Even if you look at something that looks stationary, like a piece of metal or a piece of wood, the molecules are wiggling. This is called vibrational motion, and we'll talk about this at a later time. Okay, ion dipole forces. So table salt consists of sodium ions and chloride ions arranged in a lattice structure like bricks in a wall. So we talked about this when we talked about ionic bonding. Water is a polar molecule with a negative dipole, meaning one end of the water molecule is negative, pointing toward the oxygen atom. So those would be the red spheres there. The negative oxygen side of several water molecules point toward a sodium ion. So the negative end of the waters point toward the positive sodiums. And what they do is they will go over to the salt crystal, they'll gang up on one of those positive sodium ions and pull it away. So that would be an example right there where you see two water molecules hanging on to that sodium ion there. The positive hydrogen side of several water molecules point toward the Cl, the chloride ion. So there you can see 3 or 4 different water molecules. The positive side, which is where the hydrogen is, that's the positive dipole of the water molecule, the positive side. They'll grab onto the chloride ion and pull it away from the salt crystal. When enough water molecules gang up on an Na or a Cl ion, they pull it away from the crystal lattice. Both of these effects are called ion dipole forces. So the ions are the sodium and the chloride ions, and the dipoles are the water molecules. They're polar, they have a positive end and a negative end. Dipole-dipole forces attract polar covalent molecules to each other. So hydrochloric acid, HCl, is polar because a highly polar chloride atom, it should be really a highly electronegative chloride atom, pulls the hydrogen electron towards it. So you can see there's that squiggly line with the negative and the squiggly line with the positive. That's the Greek letter delta, lowercase delta, and that represents a polar molecule. So delta negative means the polar end, or the negative end of a polar molecule, and delta plus represents the positive side of a polar molecule. So hydrochloric acid is polar the same way as water. Below, the positive hydrogen side of the HCl molecule is attracted to the negative chloride side of another HCl molecule. So that's how a dipole-dipole. You have two dipoles, that means polar molecules, and they stick to each other. Positive side of one is attracted to the negative side of another. London dispersion forces are temporary changes in the polarity of a molecule due to the random movement of electrons. Dispersion forces are how nonpolar molecules attract each other. So that may be a question that occurred to you, is if a molecule is nonpolar, how can it stick to another nonpolar molecule? Because they do. Well, you're going to see how that works. So let's look at atom number 1. It has a proton. Let's just say it's a hydrogen atom to keep it simple. It has a proton as its nucleus and it has an electron. Now that electron happens to be over on the right side of atom number 1. What that's going to do then is it's going to push the electron in atom number 2 over to the right side. In other words, the electrons are going to repel each other. So the electron in atom 1 pushes the electron in atom 2 over to the right side of atom number 2. In addition, you have a polar situation where you have the electron in atom number 1 is being weakly attracted to the proton, the nucleus, in atom number 2. So you have two effects. Electrons are being pushed over to one side, and the electron of one atom is attracted to the proton in another. That effect can repeat itself, so the electron in atom number 2 pushes the electron in atom number 3 over to the right, and then similarly the electron in atom 2 is attracted to the nucleus, to the proton in atom number 3. So what you see is these are lined up in a way that the right side of this group is more negative and the left side is more positive. Now that's temporary because those electrons are flying all over the place. However, they can tend to stay over on one side, and that's what's happening here. So when the electron in the hydrogen atom on the left moves to the right side, it pushes the second atom's electron to the right. If this effect repeats throughout many atoms, it creates a temporary polarity that attracts the atoms to each other. London dispersion forces are small but can produce strong attraction between large molecules with many electrons. So let's look at a small molecule, that's methane, CH4. So a CH4 molecule has weak London dispersion forces because it has only 10 electrons. Methane has very weak London dispersion forces and is not attracted to other methane molecules, so it forms a gas at room temperature. Alright, so if we take a bigger molecule, hydrocarbon, these are hydrocarbons, they just have carbons and hydrogens, they're nonpolar. So we take a bigger one, octane, that's C88H18. It has 66 electrons. This is strong enough to make octane a liquid with other octane molecules. And now we take one a bit bigger, this is paraffin. It's C40H82. It has 322 electrons. This many electrons form strong enough attractions to make paraffin a solid at room temperature. So again, it has to do not with the size of the molecule, and you should not say that on the AP exam that it's the size of the molecule. You should say it's the number of electrons. The one with the more electrons. You may think that's the same thing, but you can't put it in terms of size. It's not volume, it's how many electrons. Shape affects the strength of London dispersion forces. Longer, flatter hydrocarbons, such as N-pentane on the left, form stronger London dispersion forces than round neopentane molecules on the right because they fit together tighter with less space. So you can see on the left, those are going to lay right on top of each other, those molecules on the left, and form strong attractive forces. On the right, they're kind of spread out. They have branches, what are called branches, round molecules do. For that reason, the neopentane molecules over on the right, the rounded ones, actually burn faster because they have weaker London dispersion forces and they can burn much faster. Okay, hydrogen bonds. Now I call these hydrogen bond forces because they're not chemical bonds like ionic, covalent, or metallic. They're actually intermolecular forces. So for a hydrogen bond to occur, a hydrogen atom must be attached to a nitrogen, oxygen, or fluorine. So that's the first thing you have to memorize. It has to be one of those three central atoms and must be attracted to the lone pair of another nitrogen, oxygen, or fluorine atom. So let's look at the two molecules over on the left. Those are both water molecules. They have oxygen and two hydrogens as their atoms, and you can see that on the left side that proton, that hydrogen proton, is being attracted to the lone pair of the water molecule down on the lower left. Now the one on the bottom right, that's a ammonia molecule. It's NH3, and you can see that the proton from that water molecule up on the top left is being attracted to the lone pair of the ammonia molecule, the NH3. Finally, the molecule on the top right, that's hydrofluoric acid, 1 hydrogen, 1 fluorine, and you can see that the proton of the ammonia molecule is being attracted to the lone pair of the HF molecule. So they can mix and match, in other words. So it has to be a central atom of a nitrogen, oxygen, and fluorine, and it must be a hydrogen attracted to the lone pair of another. Now, why is it? Why are these significant? The answer is the electronegativity pulls the electrons towards either the oxygen, the nitrogen, or the fluorine, whichever the central atom is, enough so that that proton is kind of sticking out there. And if it's sticking out and kind of exposed, it can easily be attracted to the lone pair of another highly polar molecule, nitrogen, oxygen, and fluorine. Okay, now if you look in the center, here the hydrogen atom on a water molecule, hydrogen bonds with the lone pair on a nitrogen atom. So you're seeing that down in the center. That down there is an ammonia molecule, which is NH3, and the proton on that water molecule in the top left is bonding with the lone pair of that ammonia molecule, the NH3. It's being attracted to the lone pair on the nitrogen. That's right there. Here, a hydrogen atom on a nitrogen atom, hydrogen bonds with the lone pair on a fluorine atom. So that's a hydrofluoric acid, HF, in the upper right there, and it's being hydrogen bonded to by the proton on the nitrogen. Hydrogen bonding works because nitrogen, oxygen, and fluorine pull the electrons away from the hydrogen so completely that an exposed proton is left sticking out from the molecule. And that exposed proton can be easily attracted to a lone pair of another molecule. The hydrogen bonds of water, H2O, are stronger than the hydrogen bonds of ammonia, NH3, or hydrofluoric acid. So why is that? There is 1 hydrogen on a water molecule for each lone pair on other water molecules. That's a perfect match. So you have 2 hydrogens, 2 protons, and you have 2 lone pairs. So it's a 2-to-2 or a 1-to-1 match. The ammonia has only 1 lone pair, as you see down there, for every 3 hydrogen or protons. So it's a mismatch. You have 3 protons on 1 ammonia molecule for only 1 lone pair on another ammonia. So they're not going to bond as strongly. You've got 2 protons there. Those are plus signs, by the way. They're just tipped to the side. There's 2 protons on each nitrogen that's not going to be able to bond because there are no lone pair, not enough lone pair to bond with it. So no lone pair to bond with on those 2. Finally, the hydrofluoric acid has only 1 proton for every 3 lone pair. So again, there's a mismatch. You have too many lone pair on hydrofluoric acid for the number of protons. So since water has a perfect match, there's 1 proton for every lone pair on another water molecule, it's going to have the strongest hydrogen bonds. So no hydrogen bonds there for those 2 lone pair. So water hydrogen bonds most efficiently and has the strongest hydrogen bonds. Hydrogen bonds occur when a hydrogen atom is bonded to the 3 most electronegative second row elements, nitrogen, oxygen, and fluorine. When oxygen pulls the electrons of hydrogen toward it, an exposed hydrogen nucleus, that's a proton, is left exposed. This proton is attracted to the lone pair of another molecule with a nitrogen, oxygen, or fluorine atom. The hydrogen atom has a fairly strong attraction to the other atom, though it is not nearly as strong as its own covalent bond. So it's not going to be pulled away from its own molecule. Stronger intermolecular forces cause substances to melt and boil at higher temperatures because the molecules stick together better and don't separate as easily. So here's water. Water in vapor form or in gas form are separate molecules floating around. In liquid form, you can see they're kind of disorganized. They're pulling around each other. They're crawling all over each other. But that's why water sloshes around. You'll notice some dashed lines in there. They are creating hydrogen bonds, but those are easily broken, and they are do have dipole-dipole attractions to other water molecules. Finally, when you can take enough pressure and temperature out of water molecules, they form these real pretty crystalline structures, kind of hexagonal shaped, six-sided crystal structures, and that's what ice is. So ice is made up of water molecules in those nice, neat formations. So generally, the following is the order of strength of different intermolecular forces from weakest to strongest. London dispersion forces are the weakest because they consist of temporary dipoles, that is, electrons just pushed over to one side temporarily. All molecules, and this is important, all molecules have London dispersion forces. Dipole-dipole forces are next because they consist of the positive negative ends of electrically neutral molecules. They don't have to be electrically neutral, but in the case of water, which was our primary example, they are. Ion dipole forces are stronger because they contain a fully charged ion with the end of a molecule of the opposite charge. So you have a dipole, which is kind of sort of positive negative charge on both each end, but an ion is a full charge. It's a full 1 plus or a full 1 minus. And so that's going to be a stronger attraction. And finally, hydrogen bond forces are the strongest. Hydrogen bonds formed by water molecules being stronger than other hydrogen bonds. Alright, so that takes care of our introduction to intermolecular forces. As I said, this is a heavily tested topic on the AP exam, and we'll be doing a lot of problems and examples in this area.